Okay, class, let's talk about this last part and then we're going to do practice problems next lecture. So far, we've learned if you have a strong acid or a strong base, how to figure out the pH. If you have a weak acid or weak base, how to figure out the pH. If you have a conjugate acid or conjugate base, how to figure out the pH, yeah? So now what we're going to do, we're going to mix things up. Now, the first thing we're going to mix together, let's say we have 0.100 molar hydrochloric acid plus 0.100 molar acetic acid. So we are going to mix up these two solutions. And the question is, what would be the pH of this solution? So everything we've done so far, we haven't mixed things up, right? We're just like, this is the solution, what's the pH? This is the solution, what's the pH? Now we're going to add things together, mix things together, and then ask you what is the pH, okay? Now, when you look at this, the first thing that you should say is that, okay, hydrochloric acid is a strong acid. So I'm going to write that down. Hydrochloric acid is a strong acid. Now, acetic acid is a weak acid, okay? So I have a strong acid and I have a weak acid. That's what I'm mixing up together. Now, when you have a strong acid, for example, hydrochloric acid, you know that hydrochloric acid is going to have 100% dissociation in water, right? Every single hydrochloric acid would break up into hydronium and Cl-. Now, in this case, what I have 0.100 molar hydrochloric acid, but because it's a strong acid, every single hydrochloric acid is going to break up. So I would end up with 0.100 molar of H+. You guys following me so far? Okay. So now from that, you know how to do this because you know that the pH is going to be the minus log of the H+ concentration. And then H+ concentration in this case is 0.100 molar because this is a strong acid and every single thing would break up into ions. So then what I end up getting for the pH, I get a pH of 1. Okay, so that's my strong part, but then there's another thing going on, and on the other side, I also mix in this with a weak acid, right? I'm mixing this with a weak acid. What is my weak acid? Acetic acid. If you remember, I said we usually abbreviate HAC for acetic acid, a little bit easier. Now, it's a weak acid. So weak acid, you would have partial dissociation. So you would have an equilibrium. Nothing you've never seen before, right? You would have an equilibrium if you have a weak acid. Okay, now you also need to remember, every time we have a weak acid or base, what do we put? We put ice, right? Every time you have a weak acid or base, you usually put down the ice table. Okay, now at the beginning, what do I have? I have 0.1, give me 1 second. At the beginning, I have 0.100 molar acetic acid. You guys following me so far? Okay. Now remember, you're mixing these two together. So you have 0.100 acetic acid. But here's the tricky part about this. You're mixing it with a strong acid. Now when you have a strong acid, that means 100% dissociation. That means in that solution, I have 0.100 molar H+. Right? So I have also 0.100 molar H+. Okay, I may have lost you. I'm going to explain it again. So I'm adding these two solutions together. This is a strong acid. I'm going to have 0.100 molar H+. This one is a weak acid. I'm going to have an equilibrium. We're going to start off with 0.100 acetic acid. But since after we mix this together, I also have 0.100 H+ in this solution. Okay. Now, remember, now what we're going to do, again, the same thing as before. We're going, and then this is also 0. We're going to have minus x, x, and x. At the equilibrium, what I end up with is 0.100 minus x, 0.100 plus x, and x. You guys still following me so far? Okay, beautiful. Now again, this is a weak acid. Every time you have weak acid or base equilibrium, you have an ice table, and you also have Ka, right? You also need an Ka value. The Ka value for acetic acid, we've done it before, is 1.8 times 10 to the minus 5. Okay, and what is that going to equal to? Product over reactant, so 0.100 plus x, and x over 0.100 minus x. So then you're going to say, oh boy, this is going to be some algebra I have to do. Now here's the thing though, because this equilibrium constant is really small, whatever these two x's are is so small compared to 0.1. So whatever these two x's are is going to be so small compared to the big number that is 0.100 molar. Okay, so hopefully you follow that. So this x I can assume is 0, and this x I can also assume is 0, because compared to the 0.100 molar H plus, these two are going to be so small. Right? These two are going to be very small. Okay, now if that's the case, so if I simplify this, so I'm going to have my Ka value equal, so then what's going to happen? It's going to be 0.100 times x over 0.100. Okay, now do you guys see where I'm going with this? Do you guys see where I'm going with this? Okay, now what happens now? Oh no, this is just going to get cancelled out, right? And then the x is going to equal the Ka value. Okay, now here is what's going on. And I wanted to show you this so you can kind of see it before I just mention it to you. So hopefully you follow this, right? I have a weak acid, but I also have some H plus already in there. I do the ice table, I do the equilibrium constant, and then when I do the equilibrium constant, this is a crazy algebra I have to do, but I don't have to do a crazy algebra because I can assume these two x's are 0. Why can I assume this is x is 0? Because compared to 0.100, which is a big number, this is going to be such a tiny number that is not going to matter. That is not going to matter. Okay? So, if I want to figure out the x, again, if I do this, if I assume these two are too small, so I'm going to assume they're 0 to make my math easier. I can do that because it's going to be such a small number compared to 0.100. And then this would get cancelled out. So what can you tell me about this? What you can tell me about this is that acetic acid doesn't matter. Acetic acid doesn't matter, right? If you look over here, the hydronium concentration, the H plus concentration is 0.100 plus X. How did I get that? Right here. This is from over here, right? This is my hydronium concentration. It's going to be 0.00 plus X. Do you guys agree with that? Now, the X is not going to matter because it's going to be such a small number that we didn't even do the math for it. So the hydronium concentration is technically just 0.100. We can ignore this because this is going to be such a small number. Yeah? Okay. So here is what I was trying to get to, but I wanted to show you with the math also. Every time you have a strong acid and a weak acid added together, the strong acid is going to win. The weak acid is kind of adding a drop to an ocean. It's not going to make much difference for us to even calculate it. The same thing for the strong base and weak base. The strong base will win, to the point that we don't even need to calculate the weak acid, because whatever the weak acid is going to be like a drop in an ocean. Okay, so when I'm doing this problem, I can just ignore this as I showed you that, because we're going to assume these are the x's are 0. This would cancel out, right? The x is going to be such a small number that is not going to matter. So here would be the take-home problem, not a take-home message. Every time you have a strong acid added to the weak acid, again, I went through the math because I also wanted to show you mathematically that it really doesn't matter. What happens is that the strong acid will win. The strong acid will win. So you can ignore you can ignore the weak acid because it's going to be like a drop in an ocean. so you don't need to do the equilibrium. Okay, the same thing with a strong base. If you have a strong base added to a weak base, what's going to happen? The strong base will win. So you don't even need to do an equilibrium to figure out and then get a number. So in this case, what's going to be the pH of this solution? The pH is going to be 1. Okay, the pH is going to be 1 because again, here is going to be 0.100 plus x, but this x is such a tiny number that we're not even going to worry about it. Sounds good? Okay, strong acid and weak acid. The strong acid will win. You don't even need to do an equilibrium equation. Just do the pH for the strong acid. That was the same thing for the strong base. And hopefully I showed you here. And the reason for that is it would be like a drop in an ocean. This x is so tiny compared to 0.100 that we're not going to worry about it. Alright, so that's the first mixing things together. Now the second kind of mixing things together. Let's go over and let's show you doing a practice problem. Here is a practice problem. So read this problem. We have 1.00 liters of hydrofluoric acid is added to 750 ml of 0.10 molar sodium hydroxide. So again, we're mixing things together. The last problem, we mixed two acids together. Now, what's going on in this problem? What we're mixing together is hydrofluoric acid and sodium hydroxide. What are we mixing? What we're mixing here, we're mixing an acid and base together. So what we have an acid-base problem. So we're adding a base to an acid. We have an acid and base problem because this is added to this. Acid added to base. Now, we haven't done a problem like this before. So I'm going to spend a lot of time making sure you really understand how to do acid-base problems. First of all, when you have an acid-base reaction, is not an equilibrium. Is not an equilibrium. Yeah, when we had a just weak acid or weak base question, equilibrium. A conjugate acid, conjugate base, equilibrium. Here, acid-base reaction are not equilibrium, right? They're chemical reaction, or some of the fastest reaction in chemistry are acid-base reaction. Okay, that's the first thing. Now, when you do acid-bases, so this is number one, what you have to do, you have to use moles. When we do acid-base reaction, we have to use moles. Okay, you have to use moles. And the other thing that you have to think about is limiting reagent. So you have to use moles and you have to think about limiting reagent. And we don't use ice, we use ICF. And I'm going to go over this and then make sure you're understanding this, but I just wanted to make sure you're on the same page. So when you read a question and you go, oh, I have an acid and I have a base, bam, that's an acid-base problem. Acid-base problem is not equilibrium. I have to use moles. I have to figure out limiting reagent, and I'm going to use ICF. So far, so good? Okay. So, acid-base problem. What I have here, I have hydrofluoric acid plus sodium hydroxide, my acid-base reaction. And the way you can actually do this, we can figure out a product. Remember when we did double replacement reaction, in is with in is, out is with out is? That's what you can do. You can do a double replacement reaction. So when you have acid bases, what you can actually do, you can do a double replacement reaction. And you remember that from Chem 1A. Good old days. Double replacement reaction. So in is with in is, out is with out is. If I do in is with in is, out is with out is, what I end up getting, I would end up getting NaF, and the out is would be H plus OH. Do not write down HOH. You have to write down H2O. That is H2O. Okay. So this is my acid-base reaction. Is not an equilibrium. Okay. I did a double replacement reaction. Then what you have to do, you have to do ICF. Well, what is ICF? initial, change, final. It's not equilibrium anymore. Initial, change, and final. Okay. So here's my acid-base reaction. I'm going to do an ICF. Now, you have to deal with moles. You have to deal with moles when you have an acid-base problem. You have to deal with moles. Okay. Now, what I need to figure out, I need to figure out moles. Can I do that? Sure, I can do that. Now, what I have molarity. But if I have molarity, I can figure out moles. Don't forget, molarity is moles per liter. Always remember that molarity is moles per liter. Molarity is moles per liter. I have the molarity of hydrofluoric acid. That's 1.0 molarity. I don't have the moles, but I know it's 1.00 liters. Okay, so molarity moles per liter. I have molarity, I have volume. What I'm going to get for X, I'm going to get 1.0 moles of hydrofluoric acid. So far so good. Okay, so I got the moles of hydrofluoric acid. Now what I'm going to do, I want to come over here and I'm going to put the moles of hydrofluoric acid, which was 1.0 moles. Okay, now let's do the same thing for sodium hydroxide. Again, don't forget, molarity is moles per liter. You know that. Molarity is moles per liter. What is the molarity here? The molarity of sodium hydroxide is 0.10 molar. X, the volume is 750 ml. Don't forget, you have to convert it to liters. Okay, so if I do that, what I end up getting for X, I'm going to end up getting 0.0750 moles of sodium hydroxide. So that is moles of sodium hydroxide. Okay, so I just converted them to moles because you know that for an acid-base reaction, what you need moles. For acid-base reaction, what you need moles. Okay, so far so good. And what am I doing with sig fig? It was 750, so let me get the sig fig right? I don't need this 0 because it was only, let me do this because I should set a good example for sig fig, shouldn't I? In theory, I should. There we go. So far so good because I was only limited with 2 sig fig because this was only 2 sig fig. All right, beautiful. So now I have this. So I have the moles, and of course at the beginning, I don't have any of this. And water doesn't really matter because it's liquid. I don't have any of these at the beginning. Okay, now, so this is my initial, and I'm going to put moles for initial. Now, what's going to be the change? What's going to be the change? You know what's going to be the change. Minus X, and then I'm going to get X. Okay, now, what is going to be the change? Remember what I talked about? I said you have to care about limiting reagent. So this is not an equilibrium problem. This is an acid-base reaction. One acid will react with one base. One acid will react with one base. Now what I have 1.0 moles of hydrofluoric acid. I have 0.075 moles of sodium hydroxide. What is my limiting reagent? Tell me. You probably know it. What is my limiting reagent? My limiting reagent is going to be sodium hydroxide because I'm going to run out of that. So I can go one more, and then I have a lot of hydrofluoric acid, but I don't have sodium hydroxide. Okay, so that's my limiting reagent. So that's the one I'm going to run out of. So what is going to be my X? So my X is going to be my limiting reagent. So it's going to be 0.075 minus 0.075 and plus 0.075. I want to go slow to make sure you guys are really following that. Okay, so this was my limiting reagent. That means 0.075 moles of NaOH will react with 0.075 moles of HF. And then I have no more sodium hydroxide to react with hydrofluoric acid. Yeah? Okay. So far, so good. All right, so now F means what again? F means final. F means final because we don't have equilibrium. F is final. So my F is going to be 1.0 0.0 minus 0.075 would be 0.925. I'm going to have none of the limiting reagent left. That sounds about right. And then 0.075 moles of sodium fluoride over there. Are you guys good so far? Okay. Now, what do I end up with? What do I end up with? Okay. This is really key. What do I end up with? So after I do this acid-base reaction, here's what I'm going to end up with. Okay. So I want to actually write this down because I want to make sure you understand this. After my acid has only one A. After my acid-base reaction, I'm going to end up with what? I'm going to end up with 0.925 moles of hydrofluoric acid. I have no more sodium hydroxide because that was my limiting reagent, and 0.075 moles of sodium fluoride. This is what I end up with. Okay? All right, so now what do I got? Now what do I got? What do you have right now? I want you to look at this. What do you have right now? You have a weak acid and its conjugate. Do you guys see that? You have a weak acid and you have its conjugate, don't you? You do. That's what you end up with. So now what I'm going to do, I'm going to set up a hydrolysis. I'm going to set up a hydrolysis. Because what I end up with weak acid and its conjugate. I end up with weak acid and its conjugate. So far, so good? Okay, that's what I end up with. So far, so good? Now, here's the thing though. Here's the thing about this equilibrium. When you do equilibrium, you need molarity, right? A K equilibrium is product over reactant. It's the concentration of product over reactant. I don't have that right now. I have moles, I don't have molarity, but I need molarity for equilibrium because equilibrium constant is concentration of product over concentration of reactant. So what do I got to do now? What I got to do now, I got to figure out molarity. I have moles, but I don't have molarity. Again, what is molarity again? You know that. Molarity is moles over liter, right? Is moles over liter. So I have the moles, I can divide it by the liter. Now here's the tricky thing about it. Moles over the liter. After we mix them together, what is the new volume? So what you'd end up doing, you ended up adding 1.0 liter of hydrofluoric acid plus 0.75 liter of sodium hydroxide. Do you agree? So now your final volume is 1.75 liter is my final volume. That's my new volume, right? My final volume or my new volume. Okay, so that's the volume I need to use to figure out the molarity. So for HF, we do 0.925 moles over 1.75 liter. If I do that, I get 0.528 molar. Okay. Now the other one is 0.075 moles over 1.75 liters. What I end up getting is 0.0428 molar. You guys are following me so far? Okay. So these are the molarity because I need molarity for K equilibrium. I need molarity for K equilibrium. So I have to put molarity for K equilibrium. Yeah? Now I have an equilibrium. You know how to do this now. You're going to do an ice table. You're going to do an ice table. Okay. I know this is a big problem, but hang in there. You guys are doing really well. Now I'm going to do one ice table to do this. Okay, what is my initial? Again, I know my initial concentration will be 0.528 molar of HF, and I have 0.0428 molar of, oh, not that one, 0.0428 molar of F minus. Okay, are we good so far? All right, now the change is going to be minus x, and x. Equilibrium, 0.528 minus x, this is my x, and this is 0.0428 plus x. Okay, now I'm doing an equilibrium. This is Ka because I have H plus. Ka is going to be product over reactant, okay? Nothing we've never seen before. It would be x times 0.0428 plus x over 0.528 minus x. Nothing you've never seen before, right? In equilibrium is product over reactant. Okay. Now, to make the math easier, what we could do, and it's okay to do that, we can assume this x is 0 and we can assume this x is 0. You can do that in this class because I want the math to be a little bit easier. I don't want to focus on math right now. So for k, what was my k value? I gave you the k value. This was the k value. The k was 3.5 times 10 to the minus 4 equal is going to be x times, is going to be x times 0.0428 over 0.528. And what I'm going to do, I'm going to solve for x. You guys are following me so far? Good. If you solve for x, what you get is 0.00432. And again, as you can see, x is such a small number, it was okay that we assumed these x's were 0. So this is my x. Now, what does x represent that can help me out? What does the x represent that can help me out? Don't forget, the main thing was to try to figure out the pH, right? Now, what the x represent here, which could help me out, it represent the H plus concentration. Okay, so then that's easy. I know how to do this because to figure out the pH would be minus log of H plus concentration. You know how to do this. It would be minus log of 0.00432. Okay, now if I do that, what I get is 2.36 would be the pH. Okay, this was a big problem, and I want to make sure we're on the same page. So let's go over this again. This is the first time that we had a mixing problem where I'm adding the acid to the base. I'm adding the acid to the base. Every time you have a problem that you're adding the acid to the base, what I want you to write down immediately, I want you to go, this is an acid-base problem. Acid-base problem is basically a double replacement reaction. Double replacement reaction is not an equilibrium. It's a one-arrow reaction. Acid-base reaction are one of the fastest reactions in chemistry. So acid-base reaction is a double replacement reaction. I'm going to write the product out. Then I need to remember, it's not ICE anymore because it's not equilibrium, it's ICF, initial, change, and final. Initial, now, I need to use moles. I need to use moles because right now this is not an equilibrium. One acid, one base reacting. One acid, one base reacting. One acid, one base reacting. So this is a limiting reagent problem and I need moles. So I need to figure out moles and I put the moles over here. Then I figured out what's the limiting reagent. I have much less of sodium hydroxide than hydrofluoric acid. So I will run out of that. And my limiting reagent would be the X because I'm going to run out of that, but I have hydrofluoric acid left over. So when you do this, then you can figure out the initial, the change, and the final. And the limiting reagent is always going to be gone. So far, so good? Okay. Now what I need you to do after you do an acid-base reaction, see what's left over. What do we end with? What's left over is hydrofluoric acid and sodium fluoride. So what is left over is what we end up with is hydrofluoric acid and sodium fluoride. Now what is that? That's a weak acid conjugate kind of problem, right? Weak acid and its conjugate base kind of problem. So now we are going to do a weak acid equilibrium. Now we're going to do an equilibrium. Now when you do an equilibrium, don't forget, equilibrium you need molarity. Equilibrium you need molarity because equilibrium constant is concentration of product over reactant. So I'm going to convert the moles that are left over back to molarity. So these are my molarities. Those are my molarities. Okay. So you have the molarities now. Now you can plug it into the ICE table. So here's my ICE table, initial change and then equilibrium. I have a equilibrium constant for HF. This was given to you. So this should have been the hint how to do this problem because I gave you a Ka for HF. So always look for hints in the problem. And one of the hints is I gave you the equilibrium constant for hydrofluoric acid. So I have the Ka, product over reactant. I can assume these are 0 because Ka is a small number. And when I do that, the math is easier. I figure out X. What does X represent? Then can help me out. X represent H plus concentration, which can really help me out because I can figure out the pH. So the pH is minus log of H plus concentration, and then that's what you end up getting. Yeah? Okay. So again, we are always looking to figure out what is the H plus to figure out the pH. Okay, I need you to remember this is an acid-base problem and have this in front of you as you're doing it. What I'm going to do next time, I want you to have a practice session. I want to put up different types of problem that we've gone over. And probably this is the hardest one we've gone over. And we're going to do a sample of each type of problem that you've been exposed to. Sounds good? Okay, this was a big one. Really nice job for hanging in there with me. I will see you guys next time to do practice problems.